Okay, this is the second installment of the series on SAE J1939 Advanced Theory. What I have here is an oscilloscope trace taken from an actual real machine. So this is can high, which is in yellow with respect to ground, and can low, which is green with respect to ground. So you can imagine you could take this at like the 9-pin diagnostic connector. This is a 500K CAN bus. So this was taken using an oscilloscope. In this case, it just happens to be a picoscope. If I zoom in, I can see that I have, I can see the individual bits, if you would. I can see the dominant and the recessive state, which we talked about in the last video a little bit. So the dominant state, as I indicated, this is where it gets fun. This is where it gets a little confusing. The dominant state is one where the difference in the CAN voltage, if you recall from from looking at our schematic, whenever this switch and this switch are on, we would be in the dominant state. When both of these switches are off, we would be in the recessive state. So recessive state would be about 2.5 volts. Dominant state is going to be whatever we end up, 3.5 or so, and 1.5 on CAN high and low respectively. So going back to this, let's take a look at it. We can see if I drag these rulers down here, we can get a better idea. I can see that I'm sitting at about somewhere around 2.5 volts, not exact, but pretty close. If I look at the high level, we're not going to look at that little spike that's there at the very beginning. This is real data, so yep, it's got a little bit of noise in it, but we can tolerate that. Our high level is approximately, with respect to ground, somewhere around 4 volts. If I do the same thing down here with the low, let's take a look at it. We're sitting at the highest point where it's at, just above 2.5 volts. And if I look at how far down it's being driven, we're driving it down to something like 1.3 volts. If I then say, what's the difference in voltage? We can do that as well. If we take a look here, this is a math channel, so it's A minus B, so it's high minus low, which is, we recall, that's what the controller does. I take a look and I can see over here that I've got all the statistics here for it. So my difference in voltage is somewhere, it's about 2.9 volts. So we're well within the limits of the spec sheet that we looked at previously, assuming that this has that micro or this has that CAN transceiver or one very similar within the controller. I'm not really sure what's in this controller, but I'm sure it's something very similar to what we had on the spec sheet. So if I look at all these rulers, I'm going to go ahead and get rid of these because they get a little confusing. This is giving us the information, or this is very similar to the information that we saw in the simulation when we ran it. This is pretty cool. All right, let's get this one up there. You can see this is the reason I do like these PC-based scopes. They're very easy to use and very, for the most part, pretty intuitive. Okay, getting back to looking at the information we have here. I indicated before that a recessive state has a difference in voltage, or a VDIF, A minus B, of about 0 volts. And we can see right here, that's exactly what this purple trace is. This is a math channel, it's A minus B. Both of them are right at 2.5 volts, so it's sitting here at 0. So this is in the recessive state. Neither of those switches are on. We call this one of two things. This is either the recessive state and I'm sitting listening and waiting for something to happen, such as this CAN message. We can see there's not a lot of traffic on this bus. But if we're sitting waiting for this CAN message, we're going to be, neither of the switches would be on any of the controllers that are on the bus. So if I go back to take a look at my switches, or the analogy of the switches, neither of these FETs would be on, neither of these switches. So we're going to be sitting, all the controllers sitting listening at 2.5 volts. That once I do have a device that starts transmitting, we would then call that first bit, when we would see both of the switches come on, we're going to drive up to the 4 volts and about 1 volt in this case. And when I see both of those switches, or when both those switches come on one of the controllers, I'm not sure which controller this is, but one of these controllers came on and it's going to put a message on the CAN bus. As long as this bus is sitting idle like this, where there's nobody communicating, where we're sitting in the recessive state, as long as we're not in the middle of a message, anybody that's on the bus, I don't care who you are, it doesn't matter how important you are, you could be the communication radio, the radio, for example. If you get on the bus and you're communicating a message, a canned message, nobody can interrupt you. They can't come in and say, I'm the engine controller or I'm the transmission controller. I got a message that's more important. If you're already on the bus and you're past what we'll call arbitration, and wow, that's way down the road. We'll get into what that is. But if you're past that region and you're communicating a message, this is why CAN is fantastic. It allows that controller to finish its message. Once it's done, then other people, other controllers, maybe they have a more important message, can get on the bus. So you can imagine you're sitting in a meeting and you are not important in this meeting and you're gabbing and talking about something. Even the most important person, the president of the company, the CEO, whoever he is, he's got to wait until you're done talking. Granted, it won't be very long, but once you're done talking, then they can talk. So don't try that in real life. It's pretty bad for your career. If we look at what these zeros and ones are, we'll talk about the dominant state and the recessive state. This is a recessive state. We're not calculating it as a 0 or a 1 because it's just sitting recessive. It's quiet. It's waiting for something to happen. When we first see this go high, we call this bit, and then we would call this first bit, we would call this a logic 0. There are 2 of these logic zeros in a row on this particular message. The next thing that is transmitted is a logic 1, and there's 2 of them that happen in a row. So this is a 500K CAN bus. This is happening all very quickly. We can see that there are the time division down here, 2 microseconds per division, or each of these divisions, so 2 millionths of a second, and that's the duration of a bit at 500K on a 500K CAN bus. So if I look at this, I've got a 0. I have 2 zeros in a row, then a 1. So this is a dominant, a dominant. Both of those switches are on. Both of the switches are then turned off because we've started communicating. This recessive state is now called a logic 1. And so we have 2 of those in a row. And then in this particular message, we have a couple of more logic zeros in a row, and then we have 4 logic 1s in a row, even though those logic 1s are just sitting at this recessive state. So you can imagine what's going on in this device. To communicate, there's logic someplace that is coming in and telling this device to turn on. So we've got information. We're telling this to transmit. Here comes our information, and it tells this we either want this to be, we want to turn the switches on, or we want to turn the switches off. And in so doing, what we end up with is what we saw on the scope, this pattern. So this is recessive. This is a recessive state. This is a dominant state, and that is counted then as bits because we've started with this dominant state, and then we go back to recessive, recessive. This pattern just happens to be for this message. If you look at a different one, it would have a completely different pattern. What this is, I have no idea. I would have to take it from this binary format. I would have to put it into something called hexadecimal, something for another time. We'll look at that and we can determine kind of what the message is. But this is some more of the fundamentals of J1939 and the dominant state and the recessive state. So we can see once the message is completely all done, we finish up and we have basically some other controller that's on the bus said, in this case, I think there's only 2 controllers on this bus, indicated, yes, I saw your message. There's a whole bunch of information that's contained here. Some of this is, and it's stuff for another time, but it's the CRC. That's the cyclic redundancy check. It tells us whether or not the message has been received by the other controller. This is what it should be, is the other message, the other controller is happy with it. If it's received the same number of 1s and 0s, that CRC will be handled. So then we have a pause, like an end of frame piece here, and then once that end of frame time period, 14 microseconds, is completed, somebody else could communicate then if they wanted to. In this case, this bus is pretty idle. There's not a lot of traffic on this bus. So this is, once again, kind of using the oscilloscope, tying some of the use of the oscilloscope, not that you have to have one to understand, but it does help us with some of this theory of operation.